Today we're doing some more Calculus 2 practice problems looking at the integral test with series to determine convergence or divergence. So let's look at this series from 1 to infinity of a sub n, right? And we're trying to determine the convergence or divergence of this. What we can do is directly compare it to an integral going from 1 to infinity, an improper integral, of a function. And that function is going to be the exact same as our sequence, just maybe with an x and a dx instead. And if that integral will converge or diverge using the skills that we learned in the improper integrals video, then the series will match the convergence or divergence of that improper integral. And sometimes that improper integral will converge to a certain number, right? That's what it means to converge. It will approach a number. That doesn't mean that the series will converge to that number. It will just match the convergence of the integral. But we have a few requirements. In order to use the integral test, a sub n, our sequence, must be continuous, positive, and decreasing on this interval. So most functions are going to be continuous on that interval because all of the functions that we deal with, they are continuous on their domains, and this is in the domain of most functions that we deal with. So we're not really too concerned about the continuous part, but we do want to make sure that they're positive and decreasing. Like in this example, we want it to be decreasing. We want the first term to be bigger than the next, bigger than the next in general. Not every term. Like you can see 3/12 is actually equal to 1/4, right? 2/7. We know that 2/8 is equal to 1/4, so 2/7 is actually bigger than 1/4. Right, so it actually increases from 1/4 to 2/7. So in general, though, I bet for all of the rest of these terms, they're going to be decreasing. So we can use the integral test. We're a lot worried about the terms towards the end of the sequence when we're talking about convergence or divergence. But let's see that it can be applied. Yes, it's decreasing. Yes, it's positive. Check, check. So first of all, we need a sequence, right? What is a sub n? We can see that the top of these fractions are growing with n, right? When n equals 1, it's 1. When n equals 5, the top is 5. That's easy. What about the bottom? We have to find the pattern. You can see that if you subtract 3 from all of these denominators, we're left with this. So we have a 1 plus 3. We have a 4 plus 3. We have a 9 plus 3 and a 16 plus 3, and finally a 25 plus 3. You can see that for n equals 1, 2, 3, 4, 5, you see the pattern, it's just n squared plus 3. See, look at this term right here, n equals 4. We're going to square 4 and get 16 and add 3 to get that 19. So this pattern works for all of them. So in order to determine the convergence or divergence of this series, what we can do is directly compare it to this integral, the integral from 1 to infinity of x over x squared plus 3 dx. So with a simple u sub, let's throw in the 2, account for it with a 1/2 out front. I do have the whole video on improper integrals if this part confuses you. But we can change the bounds to the u. 1 squared plus 3 is 4. Infinity squared plus 3 is infinity. That way we won't have to plug back in our function of x, which we'll see in a minute. We have 1/2 ln, the absolute value of u, evaluated at those bounds. See, now we don't have to plug back in our function of x and plug back in x bounds if we just change the y, or change it to the u bounds. So we'll do 1/2 ln of infinity minus ln of 4 right? And we can see that this is all just going to equal infinity because ln of infinity is infinity, and infinity minus ln of 4 is still infinity. So we could say that this integral diverges, which means that the series will diverge as well. It matches the convergence or divergence of the integral that you can make with that sequence. So the integral test is pretty useful for functions just like this one, where it kind of looks like something you can easily integrate, right? But this one you might not see it right away. We can see that, first of all, we know that x squared plus 2x plus 1 will become x plus 1 squared. So if we just change all those, or how about this? We can change that to an x squared plus 2x squared plus 1. And all that's going to do is change this x to an x squared. And as you can see, that's exactly what we have right here, right? We have well, first let's make the integral. We could, in order to determine the convergence or divergence of the series, we can look at the integral from 1 to infinity of x over x to the 4 plus 2x squared plus 1, which we said could become x dx over x squared plus 1 squared. So using a little bit of algebra there. Then we'll do a u sub. U is equal to x squared plus 1, and du is equal to 2x dx. So we'll throw in the 2, account for it with the 1/2 out front, and change the bounds. Plug in 1, you'll get 2. Plug in infinity, you'll get infinity of du over u squared. So this is going to become 1/2. When you integrate 1 over u squared, you're going to get minus 1 over u, and you can check that with a derivative. And we're going to evaluate that at infinity and 2. We don't have to plug back in our function of u because we changed the bounds again. So 1/2 minus 1 over infinity minus negative 1 over 2. Right, so 1 over infinity will approach 0, and a negative 1/2 will change to a positive 1/2. So we have 1/2 times 1/2, or 1/4. So the integral converges. That just means that the series converges, right? What does it converge to? Does it converge to 1/4? No, we cannot determine what it converges to using this test. It does not converge to 1/4. We can just say that it matches the convergence of the integral test, right? So let's look at another example. How about this one? This is what we're mainly going to use the integral test for, because this almost looks like this integral right here, 1 to infinity of 1 over x squared plus 1. This is just on our formula sheet, right? We know this is going to become arctan of x evaluated at infinity and 1. Right, the derivative of arctan is this function, so the integral of that function would become arctan x. So and let's see, does this converge or diverge? Well, arctan of infinity minus arctan of 1. So there's a few ways to solve this. You could plug in a really big number instead of infinity into your calculator, and like if you do arctan of 100,000, for example, right? What it's going to give you is pi over 2. And if you plug in arctan 1 into your calculator, you're going to get pi over 4. Pi over 2 minus pi over 4 is pi over 4. So the integral converges, right? The integral converges, which must mean that the series converges as well. But I do want to touch on how you would do this, maybe without a calculator, or if the calculator was just showing an error. Well, arctan of infinity means what can you plug into tangent to get infinity? And tangent is sine over cosine, right? And if we want that to equal infinity, we want this to equal 0. What can you plug into cosine to get 0? Well, cosine of pi over 2 is 0, right? So when you plug in pi over 2 into tangent, you're basically dividing by 0. And dividing by 0 as you approach 0 will become infinity, right? So we could say that arctan of infinity is pi over 2. Same thing with arctan of 1. We want sine of something over cosine of something to equal 1. Was there anywhere on the unit circle where sine of that angle and cosine of that angle are equal to 1? Yes, at pi over 4, right? Pi over 4. And there is a domain restrictions. But sine of pi over 4 and cosine pi over 4 are both 1 over root 2, right? 1 over root 2 over 1 over root 2 is just equal to 1. So pi over 4 would be the angle that corresponds to arctan 1. Or I guess I should bring that over here. So pi over 2 minus pi over 4 is just equal to pi over 4. So the integral converges, which must mean that the series matching it converges as well. Once again, the series does not converge to pi over 4. It just matches. It just matches the convergence of the series. Right, so let's look at our final example. Proven 2 ways why the infinite series diverges. There's 2 ways to do this. One, we can just see that this is a divergent p series, right? You could say that this is n to the 1. And remember what we said from the last video, the series, or the sum from 1 to infinity of 1 over n to the p will diverge if p is less than or equal to 1. And since this is equal to 1, it must diverge by the p-series test. But the p-series originated from integrals, right? So, but we could also do this with a integral test. We could look at the integral from 1 to infinity of 1 over n, and we will see that, or I guess you could do it with n's, but we're just used to x's, so we'll stick with x. We do the integral from 1 to infinity of 1 over x dx, we are going to get ln of x evaluated at infinity and 1. So we'll get ln of infinity minus ln of 1. Ln of 1 is 0, ln of infinity is infinity. The integral diverges, therefore the series must diverge. So we proved in 2 different ways why this divergent harmonic series diverges. So that's the end of these 4 problems using the integral test to determine convergence or divergence. But I just want to show why. It was a pretty quick video, so I want to show why this is. We can prove this p-series test. If we do, it originated from the integral test. So if we do 1 over x to the p dx, what could we say that is? That is the integral of, isn't that x to the negative p? And how do we do x to an exponent? Don't we just add 1 to the exponent and divide by that new number? And now we'll plug in infinity and 1. So when we plug in infinity and 1, we're going to get infinity to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. So we don't really care about this term. This term is not going to affect the convergence or divergence. It's this term with infinity, right? This term with infinity that's going to affect the convergence or divergence of this integral. So I don't even want to look at this side. This side doesn't really matter, because that just depends on what term you start from, right? 1 or 2 or 3. But we know that those beginning terms don't really affect the convergence or divergence of our series. So we just have to think, when would this right here diverge and when would it converge? It would converge when that infinity is in the denominator and it can become a 0, right? When it can become a finite 0 versus an infinite number with that infinity up top. So when will that infinity swing to the bottom? How about when it has a negative exponent, right? In other words, add the p to the other side. When p is greater than 1 is when that infinity will swing to the bottom and the integral will converge. That's why we say that for the p series, it will diverge if it's less than or equal to 1. Otherwise, if p is greater than 1, it will converge, which we looked at in the last video. So that's where the p-series test comes from. But other than that, that is how you use the integral test to find the convergence or divergence of infinite series.